Hi everyone. So today we're going to continue our discussion of 5.2. So last video we get to define what we call gradient. So the gradient is basically what a derivative of a function of several variables is going to be. But we have yet to talk about how to find gradient. We have a definition, which is right here. Okay. But I mean, as you probably remember learning in BC calculus, having a limit definition of a derivative is just very complicated to use. And as a matter of fact, we're not going to be using this definition or this limit definition at all to find this gradient vector right here, which is what k is. But instead, we'll basically use this theorem, theorem 5.2.2. So what does theorem 5.4.2 state? It states the following. Let's say given a function f that maps from Rn to R. We know that its gradient, which is gradient of f, is vectors, is a vector in Rn. So therefore imply that gradient of f will go from Rn to Rn. Now since the gradient map into Rn, therefore it must have coordinate functions and that many coordinate functions. So what theorem 5.2.2 state is the following. So gradient of f has n coordinate function which define each of its coordinate. And here comes the important definition. The kth coordinate function for the gradient of the gradient of f is basically the partial derivative of f with respect to x sub k. Oh, actually, maybe I would say this with respect to its kth variable. So the important part about this theorem is they tie in gradient to partial derivative and therefore now allow us to actually form the gradient. So what does this theorem basically state? It states the following. If f of vector x is equal to f of x1, x2, to xn, then gradient of f of vector x would actually equal to this. All right, maybe I'll write this way, which is equal to y, so it has some kind of output. Then gradient of f, oops, missing the gradient. Then the gradient of f of vector x would equal to df over dx1 of vector x, df over dx2 of vector x, to df over dxn of vector x. So essentially I can form the gradient by simply collecting all the partial derivative together, and that form the gradient. So how about give you some specific example? Let's say we talk about an R2 function. So f map from R2 to R. And in this case, our function probably f of xy equal to z. Then the gradient of f, which is gradient of f of xy, would equal to df over dx, evaluate xy, and df over dy evaluated at xy. What if we have it in R3 function, which means f that map from R3 to R. So notice that these two dimensions are basically defining what the domain is. Then I will have a function f of x, y, z probably equal to w. And then in this case, the gradient of f of x, y, z would basically equal to df over dx of x, y, z, df over dy of x, y, z, and hey, what happened? Okay, you know what? Let me see if I can do this. Okay, it does. There you go. Now I have more room. Okay. So, df, oops, I don't know why. Oh, there's a line right here from the x. Okay, there you go. And df over dz of xyz. So that becomes the gradient. So the gradient is now just nothing more than a collection of the partial derivatives that we have. Now, let's go and give it a try. Let's see if we can do some simple example together. And that would show you how the gradient works. It's actually pretty easy as long as you know how to take the partial derivative. So let's try this one first. Let's say we're going to be given f of xyz is equal to xy plus yz plus xz. And the question I'm going to ask you to do this. I'm going to ask you to go and find me gradient of f. And we'll go find gradient of f evaluated at, I don't know, 1, 2, 3 maybe. Okay. Important to note is that this expression right here is technically the same thing as if I write this. Okay, the difference between these two is that this is kind of like function notation. So the gradient of f at 1, 2, 3. Well, this one is basically gradient of f such that the input is 1, 2, 3. So they both mean the same thing, and sometimes you see me write one way, sometimes you see me write the other way. Just make sure you understand that both of them mean the same thing. So how are we going to do this? So remember, in this case, the first thing you need to pay attention is the following. So just like, I don't know how many times I mentioned this, first thing you probably want to pay attention to is the function, what type of function it is. This function has 3 input, but it probably one single output that's xy plus yz plus xz. So therefore, we can say this. We can basically say that the function f of xyz equal to xy plus yz plus xz is basically equal to some output that we're going to call w. And because of that, you can think of f as a function that maps from R3 to R. And because of that, that implies the gradient of f maps from R3 to R3. So therefore, indicate that gradient of f is a vector in R3. That's important because that would mean that we know this vector basically have 3 things inside. So what are those 3 things? They are the partial derivative of f. So therefore, in this case, our gradient of f is actually equal to df over dx, df over dy, and df over dz. So therefore, if you have difficulty taking partial derivative, you would going to have so much trouble with this type of problem, because notice that this one problem requires me to take partial derivative 3 times. Okay, and that's how it's going to work with multivariable calculus. And you probably already kind of know this because that's how it is since chapter 1 when we first learned about vector. Instead of doing one addition, we do like whole bunch of them together, because that's how vector addition works. And if we want to do scalar multiplication, then we do a whole bunch of them, because that's how vector scalar multiplication works. Okay, and so here there's no different. When I want to find this gradient vector, I basically have to repeatedly do partial derivative with each of the independent variables. So we can definitely simply do that. So what is xy plus yz plus xc when you differentiate with respect to x? When I do that, I get y plus z. If I differentiate with respect to y, I will have x plus z. If I differentiate with respect to z, I will have y plus x, but I like to write x plus y just to keep it in alphabetical order. So that would be my gradient of f. And now let's try evaluate f at 1, 2, 3. So therefore basically just mean I plug in 1 for x, 2 for y, 3 for z. So therefore it become 2 plus 3, 1 plus 3, and 1 plus 2. So therefore it becomes 5, 4, 3. So that's my gradient vector at 1, 2, 3. So this is what we call the gradient of f, or the gradient function. This is gradient of f evaluated at 1, 2, 3, and therefore this often referred to as the gradient vector at 1, 2, 3. Are those two the same thing? Those two are not the same thing. One of them is the gradient function that has been evaluated, while the other one is just the function itself. Okay? Maybe show you another example. Maybe we'll try this one. Let's say we're going to let f of xy equal to square root 1 minus x squared minus y squared. And we're going to ask you to find gradient of f. So notice that now the question find gradient of f is basically identical to the question where I asked you to find all of this function partial derivative. Okay? Because, to find the gradient, I have to find all the partial derivative. The only difference is when I ask you to find all the partial derivative, you will indicate each partial derivative as its own answers, and you have multiple answers. In this case, you have 2 answers. But if I ask you to find gradient of f, you only get 1 answer, and that answer is a vector in R2, which consists of the 2 partial derivative. So that's the only difference. Now, however, please make sure you understand, if the question asks you for the gradient, you cannot give me 2 separate partial derivatives. Gradient, by definition, is a vector, so therefore you must present your answer as a vector. So keep that in mind. So this is pretty straightforward. So to find gradient of f, or in this case, I guess the gradient function, will basically equal to df over dx and df over dy. So it's just a matter of knowing how to differentiate this thing. So to do that correctly, what I'm going to do is the following. I'm going to first kind of rewrite f of xy equal to radical 1 minus x squared minus y squared to be just 1 minus x squared minus y squared, minus y squared to the 1/2 power. So that's what the radical stands for. So therefore now I can write out the partial derivative, which should be pretty simple. What is df over dx? So that would be 1/2 1 minus x squared minus y squared to the negative 1/2 multiplied by the derivative of this thing with respect to x. Therefore the 1 go away because it's a constant. The y squared also go away because that is also a constant. Therefore just leave me with negative 2x. And remember what I said, I do expect answer to be simplified, so therefore the 1/2 and the 2 will cancel out, and therefore leave you with this thing, negative 1 over square root 1 minus x squared minus y squared. If you take a minute to do df over dy, you find out you get the same exact result. So therefore, gradient of f would equal to the vector -1 over radical 1 minus x squared minus y squared, comma -1 over radical 1 minus x squared. Oh, I'm sorry. It's not -1, it's -x, and this is -y. So let me fix that. -x, -y. X squared minus, y squared. So that become the gradient. Now, last thing I want to talk about in this video, and I don't know I want to get into the next thing, but I do want to mention the following two theorems that are important in dealing with gradient. So remember, gradient is nothing more than just a collection of partial derivative. So with that being said, that would mean that somehow a gradient, whether a gradient exists or not, would tie into the partial derivative. So that's what these last two theorems are going to stay before we finish up the 5.2 with our last video. We have 3 videos for 5.2. Is this theorem, these two theorems. So in 5.2.3, which states the following. Let's say given f mapped from Rn to R, let's say on some kind of domain D. So therefore, it implies that D have to be within Rn. Okay? On the domain D. If all the partial derivative of f are continuous on D, then the function f is differentiable on D. Now, some of you may have a little deja vu, hopefully you do, because there is a similar theorem that you learn in BC Calculus that tie into the following things. Okay? And the theorems, I don't remember exactly what the theorem is, but then the theorem probably says something like this. If the derivative of a function is continuous, then the function f is differentiable. Okay, so meaning if f prime is continuous, then f is differentiable everywhere within the domain, which makes sense, because if f is continuous, if f prime is continuous on the domain, that will mean that f prime exists for every single point on the domain, and therefore that will mean that f is differentiable. And that's basically what this theorem says. You can have to think of the partial derivative of f is basically meaning kind of like the derivative, but just derivative with respect to each individual independent variable. The next theorem I want to show you is this one, which is 5.2.4. Which states the following. Let's say once again we're given a function f that maps from Rn to R. And once again on a specific domain D. This is what we know. If f is differentiable on D, then f is continuous on D. So that's also another theorem that you probably remember learning back in BC Calculus also, which states something like if f is differentiable, then f is continuous. And that's the idea of defining differentiability imply continuity. But remember, there is a catch to that statement, is that continuity does not imply differentiability, which is tricky, because just because a function is continuous doesn't mean that it's differentiable. But if it's differentiable, it must be continuous. Now, the last thing I want to talk to you about is the following. So what is the last thing? There's only one more thing I want to talk about in 5.2. So I want to get started so that maybe next video can be shorter. The last thing we want to talk about is this concept. And it shouldn't surprise you that we're going to talk about this concept because, as I already mentioned, every single time after we talk about derivative, we're kind of obligated to talk about this. Because the concept of derivative is directly tied into the concept of this thing. And if you guess it, if you guess tangent, you are correct. Something called tangent approximation. So what is a tangent approximation? Well, as the name suggests, approximation basically means you try to approximate something or try to guess what the value is of something. You actually have learned about tangent approximation already. You actually learned 2 of them so far. And yes, you only have learned 2 of them. And you might be thinking, wait, but don't we have 4 tangent formulas by now? And you are correct. You have 1 tangent formula, which is tangent line formula from BC calculus, 1 tangent formula in 4.1, which is a tangent line in parametric form, and then a tangent plane formula in 4.3, and then another tangent plane formula, which is parametric in 4.4. But yet I only say 2. The reason why, because the following. When we refer to this as tangent approximation here, we're defining something that is tied into real value function. So therefore, there are only 2 formulas of the 4 formula deal with real value function. And they are, in BC calculus, you learned something called the local linear approximation. Which uses the tangent line, at a certain point x sub 0 to approximate f of x near x sub 0. And that's referred to as local linear approximation. And there's a formula for that, so I would like to show you what the formula is. The formula is this, so I'm going to use the capital letter T to indicate tangent approximation. In this case, local linear approximation uses a tangent line. And that approximation is this, T of x is equal to f of x sub 0 plus f prime of x sub 0, x minus x sub 0. And some of you may automatically just have a deja vu because you've seen this. This expression is what we call the tangent line in our definition of differentiability for function map from R to R, right there. Okay, so that means that when we define something that's differentiable, it must have some kind of tangent approximation that exists. And in order for this tangent approximation to exist, it must have this special value, which is called the slope of the tangent. So that's how all of them tie together. So that's referred to tangent approximation. If you want to think about it, it's also basically the tangent line at x sub 0. So this thing right here is called tangent approximation. At x sub 0, but it also referred to as the tangent line at x sub 0 if you want. Both of them same thing. Now, however, we are actually going to slowly move away from using a geometrical destination to what we're doing, because sometimes the geometry is something that we don't really care about because we can't visualize it, especially in high dimension. However, for lower dimension like R2 and R3, we're still likely to call them tangent line and tangent plane. But in high dimension, we'll probably just go generically call them tangent approximation. Okay. Now, I guess the last I want to do is let's talk about what else do we know. So in 4.3, we learned the following. We learned that we can form a tangent plane. In 4.3, let's say we're given a function f that maps from R2 to R. The equation of the tangent planes at, let's say, x sub 0, y sub 0 is given by this formula. And I will modify this formula slightly. If you recall, the formula says z equal to, but I'm going to call this, well, I'm going to call this z equal to also, but z equal to t of xy, which is equal to f of x sub 0, y sub 0, plus df over dx evaluated at x sub 0, y sub 0, multiplied by x minus x sub 0, plus df over dy evaluated at x sub 0, y sub 0, multiplied by y minus y sub 0. So that is a tangent plane, which actually also referred to as a tangent approximation. Which is also referred to as the tangent plane. So those two things are actually the same thing in this case. Now, notice I did say in this case, because can those two things not be the same? Yes. And we'll talk about that later on when we get to it, but just not right now. So in this case, these two things are actually exactly the same. Now, the only difference that I'm going to refer to is the following. Oh, as a matter of fact, I'm probably going to write this, I'm going to call this y, because that's the output. And some of you probably remember that's what your tangent formula is. The only difference between tangent approximation versus tangent plane or tangent line is probably the following. In tangent approximation, you usually would define them more or less as a function. It has an output on one side and the formula on the other side, and they are defined kind of explicitly. Okay, so therefore tangent approximation, we usually write them out explicitly. Or maybe I'll write it this way. Maybe I just write down the bottom. So one of the differences between these two things is this. For tangent approximation, we will define them more or less explicitly. Meaning it usually would be t of x equal to something, 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 or t of xy equal to something, something, something. So that's how we write them. We have the function by itself, and then have the formula on this side. Then how about what happened to tangent, if you want to talk about them as tangent lines or tangent planes, then we will usually, we will represent them in what we call standard form. So instead of using t of something, we'll probably define them as a variable. So therefore, like in the case right here for tangent line, if I say y equal to and then I kind of put it into mx plus b form, then I would be representing the tangent line, not as a tangent approximation. Same thing happened here. If I call it t of xy, then most likely kind of refer to it as a tangent approximation. But if I say z equal to, or better yet, put in as some kind of ax plus by plus cc equal to d, then I would represent as a tangent plane. And you might be thinking, what's the difference between the two? Well, functionally, the difference is one of them is a geometrical object, and usually when you put it into that form, you are basically intend to draw them as a graph, while tangent approximation is more an algebraic object where we use it to approximate value, so we use it to evaluate. So therefore, it's more about input-output versus a geometrical object. So that's usually the difference between the two. Unfortunately, that's all the time I got for today, so we'll continue on talking about tangent approximation. As you probably suspect, the two tangent approximation that we have right now, this first one right here, for local linear approximation, I forgot to write that down, that's for function f that map from R to R, and then the tangent plane formula in 4.3 is for R2 to R, so you can think of like the next thing I want to talk to you about will probably be what happen if it's R3 to R or R4 to R. How do we generalize this formula to something that we can use for any dimension? So that will be what we're going to talk about in the next video, which is the last video in 5.2. All right, I'll talk to you guys later. Bye-bye.